All right, so I'm going to start with some recent statistics. These are the 10 hottest years on record for the United States. So this doesn't include 2018. You can see almost all of them come after 2010. We've got 2012, 2016, 2017, 2015, and actually 2018 came in fourth, so we'd go in right there. July of 2019 was the hottest globally on record. If we look a little bit closer to home in Seattle, these are the 5 hottest years on record since 1948 as recorded at SeaTac. And we see kind of the same trend. Except for 1992, they've all occurred since 2014. And you remember, this past summer was a little different, but the few before that were pretty hot around here. So some of these hot and dry summers resulted in a lot of fire. 2014 was a record we had the largest wildfire in Washington state history, the Carlton Complex. 2015, you probably remember, that was a very hot and dry summer after a winter with very low snowpack. And you can see we had over 1.7 million acres burned in Oregon and Washington. And this was a satellite image in August of 2015. And that year we also had a very unusual fire, if you remember, on the Olympic Peninsula in the temperate rainforest. So what's going on here? Basically we have a bit too much carbon dioxide in our atmosphere. So this shows carbon dioxide levels from 1960 to 2020. You see this very rapid increase. This is as measured at Mauna Loa Observatory in Hawaii. So we're now at 409 parts per million. And in 1850, we were at 260. A rapid increase since the Industrial Revolution. Now, carbon dioxide and other greenhouse gases, they're not necessarily a bad thing. In fact, they keep our Earth from being too cold. The problem is we just have a bit too much, and so the carbon dioxide is trapping more heat and raising our temperatures. So if you think of a Christmas light bulb, it's about in the order of 2.3 watts. And when we talk about climate change, you often hear this term radiative forcing. And that's kind of how much we're pushing the Earth's energy balance out of whack and increasing the amount of heat being trapped by the atmosphere. If you think about that light bulb, we often talk about radiative forcing in watts per square meter. So if you think about one light bulb per square meter, that's about how much we've increased temperatures so far since the Industrial Revolution. It's about 2.3 watts per meter squared. But times 500 trillion for the whole Earth. Going forward in 2100, you can think about as almost 4 of these light bulbs per square meter. So one of the projections for the future that they think is fairly plausible if we don't do anything about reducing our carbon dioxide emissions is 8.5 watts per meter squared. That's kind of our worst case scenario for warming over the surface of the Earth. So here's some projection or some trends in temperature. Again, these are since about 1850. And you can see temperatures really started increasing in about the early 80s. And we go back to some of our record years here that have all been in the last decade or so. So this is a look at our region and how much temperatures have changed. So each of these dots shows the size of the dot shows the degree of the trend. So the bigger dots are larger trends. We have the blue dots are cooler. You can see there are a few of those, but the vast majority are these red dots and go from 0.9 to 3.6 degrees Fahrenheit increases. So over our whole region, we've had about a 1.5 degree Fahrenheit increase in temperature since 1920. You can see that warming is at almost every station. The winters the temperatures have increased faster than summer, and the extreme cold conditions have become rarer. And those minimum temperatures rose faster than maximum. So this is looking out into the future. We've got Fahrenheit here on this axis, and we've got the observed in the black line for historical, and then projections from global climate models for the future. And we have two different scenarios here, and they get back to that radiative forcing concept. So RCP 4.5 is expected to have that 4.5 watts per meter squared warming, where that 8.5 is 8.5 watts per meter squared. So there are different scenarios for what we expect in terms of carbon dioxide and warming. The blue suggesting that we're going to do something about carbon dioxide emissions and pretty quickly. The red is pretty much business as usual. You can see they pretty much track each other closely, at least the mean, till about 2050. And that's when we see big differences between the two scenarios, with this worst case scenario in the kind of 8 to 14 degree Fahrenheit increases in temperature. So what about precipitation? Well, I'm not even going to show you that figure because it's frankly all over the place. And we're really not as good at projecting future precipitation. Temperature trends, very certain about. Precipitation, not so much. Most models project for this region an increase in the winter in the total amount of precipitation. Summer is more uncertain, but notably not many of them project more precipitation for the summer. So it's kind of like a coin flip on the precipitation. So what will our future feel like? So in Olympia, Washington, in terms of average annual temperature, we're looking at something more like Sacramento, California. So what do we know? We know there is a natural greenhouse effect. It's a good thing. But we're pushing it a little bit too far with our increases in carbon dioxide. We know we've already seen effects of changing climate in the last few decades. And there's more to come, more warming to come. So we also know that these climate changes are going to affect other ecosystem processes, like the hydrologic cycle, plant establishment, growth and mortality, and also disturbance, forest disturbance. So I'm going to talk a bit more about the hydrologic cycle and disturbance, and then Dave's going to get into the plant part of it more. So starting with some snowpack, this is the South Cascade Glacier. We have the glacier in 1928, and again in 2016. And you can see down in this portion where it's retracted. We've seen that almost every glacier in the Cascade Range has retreated over the last century. And in the North Cascades, we've had a decrease of about 46% of glacial area. Same story on the Olympics. So this is a look at our snowpack trends for the western U.S. Again, we have these kind of circles, and the size of the circle indicates how much reduction in snowpack we've seen. You see a few blue here and there, especially at high elevation locations. But overall, we've seen a dramatic decrease in snowpack. It's as measured in something called snow water equivalent, which they usually measure about the beginning of April and indicates how much water we'll get from snowpack over the course of the year. So we've seen a shift from places that were really snow dominated in the winter historically to more mixed rain and snow or just rain. And here's another look at that concept. So these are different kinds of watersheds. And historically, you can see we had some along the coast. We had these green watersheds, which were mostly rain dominated. We had a lot of area in this mixed or transitional rain and snow area. And then in our high elevations, we had these snow-dominated locations in the North Cascades and in the Rockies there. And in the future, we expect that to shift a bit. So this is in the 2040s for two different scenarios and 2080s. And you can see by the 2080s, we've got a lot more green and some areas that used to be more snow-dominated becoming more mixed rain and snow. So what does this mean? This affects how streamflow happens over the course of the year. So here in Chehalis, this is a Chehalis River. This is a rain-dominated watershed. It always has been. And so you see the patterns we have this is flows from October through September, the water year. So as our rainfall increases in the winter, we get more flow. And then in the spring and summer, you can see that goes down to lower levels. And it basically follows the patterns of rainfall. We go to the Olympic Peninsula in a place like the Elwha River. That's a little different. This is more of a transitional mixed rain and snow-dominated watershed. So what happens here is we'll start with the black line, which is historical. We have increases in the winter again, but not quite as much. They're kind of, because we have a lot of water in Snowpack, so that the peaks aren't quite as high. And then we have sustained flow as that Snowpack runs off, and then a decrease when we lose the snowpack in the summer. If we look into the future, what happens when we lose that snowpack, so we have got 2020s in blue, 2040s in green, 2080s in red, is that we get a much higher peak because we don't have the water in that snowpack, and then it runs off earlier, and we have low flows earlier in the season. We don't have that sustained flow. So what that means is that we could have more floods in the winter. We saw that higher peak. We're also expecting more intense rainfall events in the winter. So more precipitation coming in fewer, more extreme rainfall events. And so we have here projections for Washington, or for the Pacific Northwest for flood. And you see the larger red dots are an increase in that risk of flooding over time. We have a couple examples of what can happen around here when we have these hydrologic extremes. This was in 2009. We had a pretty intense rainfall event, very warm temperatures, and we had rain on snow. And that resulted in a lot of damage in this part of the world. Also up on Blewett Pass, when you get these flood events, we have a lot of infrastructure damage, especially when we have roads right next to streams. Unfortunately, what this also means, even though we have more water in the winter, we have these, that runoff happen earlier. So we have also lower low stream flows. And we expect that across the Pacific Northwest that we're going to have lower stream flows earlier in the season. And again, these larger red dots indicate greater reduction in stream flows in the winter. And this has implications for salmon, our cold water adapted fish species. So this is a look at projections for air temperature and then stream temperature between the historical period and then 2020s, 2040s, and 2080s. So each dot is a projection for stream temperature. And there is some buffering between the air temperature and the stream temperature, but when we have higher air temperatures and also lower levels of water in the streams, then we get big increases in the stream temperatures, which can be really stressful for salmon and even in some extremes fatal for salmon. So our big concern here is these extreme events, these extreme low flows, these flood events, and also other disturbance events like fire. And it's not necessarily the average change in these conditions. It's more basically the tails. So a kind of shift in, remember your standard bell curve with the mean and the standard deviation. A shift in one standard deviation could mean a change in what we think of as maybe a 1 in 40 year event shifts to a 1 in 6 year event. So it's all about that tail and what might happen at that tail end. So a couple of examples of kind of extreme situations we've seen recently. One, again, was that 2015 year where we had the entire state of Washington in either severe or extreme drought conditions. And scientists think that that 2015 year might be an example of what climate change might mean in the future. So we had almost normal precipitation that year, but it almost all came as rain instead of snow. And so extremely low snowpacks. Olympic Peninsula was about 10% of normal. Cascades are very low. And then we had a really hot and dry summer on top of that. And we remember what fires, some around here, but in other parts of the world, mean for air quality. We go here, and then again, 2018 was another very dry year. So we had a couple very, very dry years in a row here. Now, this isn't necessarily odd when we think about the whole historical period. So droughts used to be a lot more common. This is from the Columbia River, kind of reconstructing flows. It's some pretty major drought events that lasted. You can see one of these lasted for many years. So we might see a bit more of that, what happened in the past in terms of drought. And drought also has effects on a couple different disturbances. One being insects. So this guy is a mountain pine beetle, and they've done very well with warmer temperatures in a lot of part of the world. It's increased their reproductive rate, and it's allowed them to be in locations that they weren't historically. And so this is a map of mountain pine beetle outbreaks since 1990. You can see we've had quite a bit in the Cascades of Oregon and Washington, but British Columbia was hit very hard with the lodgepole pine, and there are a lot of parts of the Rocky Mountain region that have been hit very hard by mountain pine beetle outbreaks. And over 50 million acres since that time. So this is a look closer to home at the Okanagan-Wenatchee National Forest, and these are the trees killed in the millions since 1980. And you can see there's a pretty major 10, 15 year period where we've had a lot of mortality from mountain pine beetle in that forest. So again, going back to fire, what are we expecting in terms of fire in these climate changes? So we've had a couple of interesting events even on the west side here in the last few years, one of them being in Anacortes in 2016, another in Halem in 2015. And overall, in that 2015 year, Washington State had over 1,500 fires, about 1 million acres burned. The costs of suppression are astronomical, and a lot of large economic losses in rural communities. But in the future, we expect to have more of these years where we have a lot of fire across the region. This is because when we have those warm and dry conditions, we have more water evaporating from the landscape, and we have drier fuels, large areas with really low fuel moisture. So when there is that ignition, fire can take right off. And so we get kind of this regional synchronization, lots of fires across the region. And we know that more fires mean more smoke. And we remember these last few pretty smoky years. We got a break this summer, but the fires, we had fires in California and British Columbia last year, made for a pretty smoky region. And we're actually areas where wildfires are colliding. Different fire footprints are kind of running into each other. So this is an area around in southwest Washington, around Mount Adams here. And there's a location here where it has burned 3 times since 2008. And that's what it looks like now. Not much left. We're expecting more of that in the future as we get more area burned and kind of fires running into each other. And that means we're going to have some interactions between fires and insect outbreaks, and other invasive species and pathogens as well. And we might have some surprises when we have these interactions. So this was supposed to be a video. I don't know if it's going to work for us. Do I keep clicking? No, it didn't work. No. What it was supposed to show you is where we've had all these wildfires and insect outbreaks across the region, and how they've overlapped, even since in the last 20 years or so. Okay, so projections for the future. These are projected increases in median area burn with a 1 degree Celsius increase in temperature, which is about 2 degrees Fahrenheit. So overall, across the western U.S., we're expecting annual area burn to be about 2 to 3 times higher than what it was historically. And this can affect something we call stress complexes. So we have warming, we have higher temperatures, more drought, we have more fire, and then we also have bark beetles and defoliators in that system interacting. And so we have, fuel accumulation with fire suppression, more large fires, and it can all interact to really affect species composition, including our invasive species that we don't want. So Dave's going to get a bit more into this, but just a summary. Overall, we're very certain we're going to have higher temperatures in the future. There will be more wildfire, less snowpack, and less water available in the summer. We have less certainty about precipitation and what we'll see for patterns there. We do expect more extreme events in terms of drought, wildfire, insects, and these are likely to have the biggest effect on our forests. And we may see things creep along for a while, but after about 2050, that's when we expect to see more major changes. And there will likely be surprises. Again, those interactions. With that, I'll turn it over to Dave, unless there are any quick questions now before we transition. Yeah?
Somewhere around your 12th slide, you showed trends in temperature. Can you find that again, please?
Sure. I'm going to have to flip back because I can't see the screen here. But I'll get back there. I'll get there. A lot of clicking. There we go.
One more.
One more? This one?
No, one more.
That one?
That one.
Okay.
I couldn't remember if you said global or if it was local.
This is global.
Yes. Okay.
Yes. Mm-hmm. Yeah?
If you could magically create that same chart going back 1,000 years, over 3,000 years.
We see trends over time, some warm periods, cool periods, but this increase is unusual. The degree of what's most unusual is this: the rapid increase in carbon dioxide and the levels of carbon dioxide we're at now compared to historical periods. Even the long paleo ice core records. Mm-hmm.
Traditionally, over time, was there always a correlation between the temperature and the CO2 content?
Yes. Yeah. There are feedbacks between the ocean and atmosphere. I don't know that sea level rise itself is going to affect temperature. Not that I know of. Disappearing ice, yes. So once that ice goes and the glaciers go, then we could see more rapid warming. Yeah? Uh-huh. Well, we have some projections here for the increases in flooding, but again, it goes back to that tail. You know, we think of floods in, you know, the 25-year flood or the 50-year flood, but when we see that shift in distribution, we're more likely to see those extreme events. So that 25-year flood might now occur every 10 years. And we've seen that across the country, that's been happening. These more extreme events that are only supposed to happen every 100 years or so are happening every 5. And we can expect that in general. Some places more than others. Again, those places where we see that shift between what was mostly rain or mostly snow or a mix of snow to just rain are likely to see that more than some other places.
I've heard that methane can be up to 30 times more damaging than CO2.
Mm-hmm.
I assume methane percentages are also increasing, and is there a way naturally to pull methane out of the atmosphere?
No, not that I know of. If you know of one, let me know. It would be the silver bullet. I know there is research going on, and hoping that we'll have some kind of technological fix, but it doesn't exist yet. All right. Yeah.
In my experience, in all bad, there's some good. So
Sure.
we haven't talked about potential good.
There is potential good.
Is there any potential good?
Oh, well, you can think of a few good things. I mean, we might have some nice warmer springs. People can get out and road bike in maybe the middle of the winter up in the mountains. I mean, there are pros and cons. The recreation season might be for summer recreation might be a bit longer. Might be able to get out when you couldn't before, or get up to elevations where you couldn't before.
More carbon help the trees grow better?
There may be some carbon dioxide fertilization, but exactly how much that goes, it's a little uncertain. There are probably other limiting factors that are going to keep that from greening our globe with climate change.
So what are the effects of the change in stream flow on things like riparians, and what's expected to
Yeah, probably not so much here on the west side, but on the east side, in drier environments, if we have much lower stream flow in the summer, it's probably going to shrink that area that gets, you know, a lot of water. We might get actually a shrinking of the riparian zone, or those really wet-loving species that are along the stream, which can have effects on shade.
So would it also have effect on things like the cottonwood in there for time of the treaty, and a lot of those goes into
Yeah, potentially.
What was the question?
The question was about riparian areas and how the lower stream flows might affect them, and cottonwood in particular.